This is the screencast for section 6.1, example 9, Euler's method. So in example 7, I'm just going to read this to you. In example 7, we graph the particular solution to an initial value problem by first producing the slope field and then finding a smooth curve through the slope field that passed through the given point. So we actually could have graphed the particular solution directly, so not by using those little mini tangents, but starting at a certain point and piecing together little line segments according to those slopes. So similar to what we did with the slope field, but now instead we could do it point by point. Well, that's what Euler's method is all about. So let f be the function that satisfies the initial value problem in example 6. So that is dy dx equals x plus y. And f of 2 equals 0. So they give you a point to start out with. Use Euler's method and increments of delta x equals 0.2 to approximate f of 3. So we are going to, if we're going to change x by 0.2, that means we're going to use f of 2, f of 0.2, f of 0.4, f of 0.6, f of 0.8, etc. until we get to f of 3. All right, so let's start out first with 2 comma 0. So we start at the point 2 comma 0, which then the derivative at that point is 2. Plug in 2 for x, 0 for y. Now we said that the change in x is going to be 0.2 that was given to us by the problem. Well then, remember, the change in y over change in x is dy dx. So if I multiply both sides by change in x, I get that the change in y would be 0.4. So in other words, 2 times 0.2. Alright, so now let's change the x value by our delta x and change the y value by our delta y, and then we get 2.2 comma 0.4. So instead of 2 comma 0, it's 2.2, we changed x by 0.2, and instead of 0 for y, it's 0.4, we changed the y by 0.4. Now we're going to use that point. So starting with 2.2 comma 0.4, we need to find a new dy dx. What is our derivative at that point? Oh, and by the way, we're over here on the graph starting at the point 2 comma 0. Now we have a new point to draw, 2.2 comma 0.4. So we're starting to draw this graph, and you can kind of see it's a little off from the actual antiderivative of x plus y, but we're going to keep going. All right, so now dy dx at 2.2 comma 0.4 is 2.6, so 2.2 plus 0.4. Add the x and y coordinates together. Our change in x is still 0.2 because that was given to us in the original problem. And now dy dx then, the change in y is going to be dy dx times delta x, so in this case 0.52. Again, delta x 0.2 times our derivative 2.6, so 0.52. So now if we take our x coordinate and add 0.2 and then our y coordinate and add 0.52, our new point is 2.4 comma 0.92. So that's up here. So we're starting again to get a little bit off the curve. It's a little bit less accurate as we go out here, and this won't be a very accurate method, but it is going to be at least an estimate. All right, so keep going. Now we're at 2.4 comma 0.92. Calculate dy dx. Our delta x stays the same. We can figure out from those two that our change in y is 0.664. Change the x and y coordinates, and we have our, yet again, another point, 2.6 comma 1.584. Now we're going to take that point, find the derivative at that point, use the change in y and change in x at that location to get our new point, 2.8 comma 2.4208. And then finally, 2.8 comma 2.4208 delta dy dx is 5.2208. Delta x stays the same. Calculate delta y, and we get our estimate then at the point 3, which is what our question was asking us for. Use Euler's method and the increments of delta x equals 0.2 to approximate f of 3. So we can say that f of 3 is approximately 3.46496. The now try problem number 41 says use Euler's methods with increments of delta x equals 0.1 to approximate the value of y when x equals 1.3. So dy dx equals x minus 1, so it's not dependent on the y coordinate this time, and y equals 2 when x equals 1. So that's going to be the point that we start out with, 1, 2. By the way, on an AP exam, this will likely be a show your work problem, and it will likely have a delta x of like something a little bit simpler, 0.5 maybe, or 1, but and only about 3 steps like this to get to your actual approximation. Some of the problems in your classwork might get a little bit more difficult just because we're learning the process. Better to have it easier on the test than harder. All right, so for 1, 2, our dy dx, so our slope at that exact point, is 0. So we're going to, our delta x, the problem gave us, is 0.1. So we're going to change our x by 0.1, but then our y by 0, and we have 1.1, 2. All right, so now we're going to start with that point, find the derivative at that point, and now the derivative of the slope at that point is 0.1. So our delta x is going to be 0.1 because the problem gave that to us. But now if we take dy dx times delta x, we get 0.01. And then we're going to change our x coordinate by 0.1 and our y coordinate by 0.01. And I get 1.2, 2.01 as the next point to start with. And now we're going to calculate the derivative at that point. Delta x stays at 0.1. Our change in y is now going to be 0.02. So our final estimation is that f of 1.3 is about 2.03. Now in this case, I can take the antiderivative. Dy equals x minus 1 dx, get the differential dy. Take the antiderivative, y equals, let's see, that's going to be 1/2 x squared minus x, and then plus c. We were given a point this passes through, 1, 2. And just to show you how accurate this Euler's method is, actual f of 1.3 is 2.045 instead of 2.03. So pretty close.